Hello everyone, Mr. Minix my name, math is my game. I apologize in advance if you cannot understand what I say, so I guess it's a good thing that I'll be writing most of this. In my Algebra 2 class, here we are, we're looking at Chapter 6, Section 6. The title is Function Operations. Function Operations. And we're actually splitting this up into 2 days. Today, we're just going to be looking at well, not just. We're going to look at 4 operations. Tomorrow we'll be looking at the part that comes after the and. The other part of this section is composite functions. And to give any kind of justice to talking about composite functions, it takes at least 35 to 50 minutes. So I thought it would be prudent to split this up into 2 days. So there will not be printed homework tonight. The Math Excel homework, you can certainly get online and try that. But the composite stuff, you probably have no clue how to do that. So what we're talking about then is addition. We're talking about subtraction. And we're talking about multiplication. Okay. There's actually a 4th operation we're going to be talking about, and that's division. But a different set of rules applies when we're talking about functions. Okay. You're probably baffled as to why we skipped over Chapter 6, Section 2, 3, 4, and 5. If you remember right, we were in Chapter 7. We just finished exponential functions. And we were going to start logarithms, but before we can do logarithms, we need inverse functions. And before we can talk about inverse functions, we need to talk about composite functions. So that's why we're skipping around as much as we are. I know it seems kind of confusing, but so let's just look at example number 1 here. Example 1, find f of x plus g of x for f of x equals x plus 2. And g of x equals x squared plus 3x minus 7. So the good news about this particular section is it's really not going to be that bad. At least half of it shouldn't be that bad. We're asked to add 2 functions together. The function f is defined by x plus 2. The function g is defined by x squared plus 3x minus 7. Making a few substitutions, I bet we could come up with the answer. What do we come up with here for f of x plus g of x, what that's equal to? F of x plus g of x would equal what? Anybody think they got this one figured out? Yeah. X squared plus how many x? Not plus 2x. Plus 4x, and then what? And then minus 5. Okay, so that would be it. That's our answer right there. That's it. In case you're wondering where we got that from, we could basically just combine like terms. X squared doesn't have any like terms. If we look at g of x, it's got 3x in it. F of x has got 1x. 3x plus 1x is where we get the 4x from. And then if we look at g of x, it's got a negative 7. F of x has got a 2. Negative 7 plus 2 is where that negative 5 comes from. So that's it. What do we think? Okay. Well, let's go to example 2. For f of x equals x cubed minus 8, and g of x equals x squared minus 2, find f of x minus g of x and g of x minus f of x. So before we go finding both of these, are they going to be the same or are they going to be different? The answers. They're going to be different. And if you think about it, remember what we said about adding things. When we add things, there's this commutative property, so the order that we add doesn't matter. But when we subtract things, the order does matter, okay? So let's go ahead and see how different these are going to be. When we take f of x, oh, I meant to make that a different color. F of x take away g of x, that's going to be what? X minus 10. Well, with the exponents, remember, x cubed and x squared are not like terms, so we can't combine x cubes and x squareds. So we're going to have x cubed minus x squared, good. And then, is it going to be minus 10? Minus 6, because it's minus 8 minus minus 2. Minus 8 minus minus 2 is going to make that a minus 6. Okay. When we go the other way to g of x, take away f of x. And again, since these are polynomials, I didn't mention it before, so I shouldn't say again. But since these are polynomials, we should put the terms in descending order by degree. So let's see, g of x minus f of x. It's not going to be x cubed. We're going to start with the x cubed term, but it's not going to be positive 1x cubed. It's going to be negative x cubed because we're subtracting that quantity. So it's going to be negative x cubed plus x squared. Good. And then g of x has a negative 2, and then when we minus the minus 8, it's going to be plus 8, so it's going to be plus 6. So how do those two answers differ? They're the inverse isn't quite the right word to use here, but they're the opposites, right? The signs are just all opposite, right? Okay. Any questions so far? Comments? Concerns? Short debates? Long debates? Let's try another one. Let's go to example number 3. For f of x equals x plus 2 and g of x equals x minus 3, find f of x times g of x. If you're good at foiling, you would find this one right away. F of x times g of x equals x squared plus negative x or minus x in the middle, good, and then minus 6 on the end, good. Okay, I know I'm skipping a few steps in this, and I hope that at this point in time everybody's okay with that. I'm not skipping them to confuse anybody. I am skipping them because these are all operations that you should be pretty comfortable with at this point, I would hope. Okay, I would hope. Well, that's adding, that's subtracting, that's multiplying. On to the good stuff? Well, we're not just ready for it exactly just yet. Because now what we got to do is we got to talk about this D word. We got to talk about the domain. Okay? The domain is the set of all possible x values. Okay, so what I'd like to do is look at several functions and talk about the domain of each one. Because one of the most difficult pieces of this section for most students to get is the domain. Okay, so maybe we should just look at y equals x for a minute. When we graph that function, it's a direct variation, goes through the origin, looks like that. All right? Does anybody recall the domain of that? The domain is the set of all possible x values. So when we talk about its domain, we could say it's the set of all the x's such that x is what? I'm going to write this as many ways as I can just to show you some different notation for domain. So literally translated, this means the set of, and then this means all x's, and then this means such that. So it's the set of all x's such that And then this means x is what? Now, I heard somebody say infinity. That's part of it. When we use interval notation, we put the small number on the left. We put the large number on the right. In fact, we put the smallest number that x could take on the left, the largest number that x could take on the right. So what are we going to use in that notation? We're going to use the infinity in this notation. So the largest x value would be positive infinity. What about the smallest x value? Negative infinity. We put a comma to separate the two, and we use either parentheses or brackets. Parentheses because we can never actually get to infinity. Okay, so let me highlight that. If it was negative infinity to 4, would you put brackets on the 4? If the graph went through the point 4, then you would. If the graph didn't go through the point 4, then you would use a parenthesis. Okay. So this right here is called interval notation. Interval notation. Going back up to this one that we started on, the set notation. So this is set notation here. Set notation. It's the set of all x's such that x, we use this weird E symbol, and then we use this weird R symbol, and then we close off the set. Translating the rest of that means x is an element of, and then this R here means the set of real numbers. So that's just a fancy way of saying negative to positive infinity. X could be any real number. In words, we could say that as x is all real numbers. Some textbooks do that. Sometimes Math Excel does that. The whole reason I'm showing you all these notations is because you will see different ones in different textbooks depending on what class you take. Okay. So that's just the domain of that linear function. Let's look at the domain of y equals x squared. What's the domain of that? All positive numbers? 0 to infinity? I'm hearing 0 to infinity. I'm hearing all positive numbers. So this would be all positive numbers. The one above it would be 0 to infinity. If that were the case, the graph would look like this, but it doesn't. The graph does, what's that? What to negative infinity? 0 to negative infinity? 0 to negative infinity? Well, we can't write that like that because we got to put the small number on the left. Negative infinity to 0, 0 to infinity. Well, do we need to do that? No, we don't even need all that. Isn't this one just negative to positive infinity again? Right? It is. Okay? This one's just negative to positive infinity because there's no holes, there's no breaks, there's no jumps in the graph of that. Okay? So the domain of that is all real numbers again. In fact, what did we say about any polynomial, about its domain? I tell you one thing, we didn't find the answer on our cell phone. What did we say about the domain of any polynomial? So what do we say about any polynomial? What do we say about any polynomial, its domain? It's, yeah, all real numbers. The domain of any polynomial is all real numbers. Okay? The end behavior, this one's going to be up and up. I don't know what the rest of it looks like, so that really doesn't matter. So you're probably asking yourself at this point, self, are there any functions that don't have a domain like that? Now, we have to put the cart before the horse. Are we okay with that? What kind of cart is it? It's one of those Amish buggies that has the lights on it and the triangle on the back and the subwoofers in the back. I know a couple jokes, but I'm not going to tell them because they might be offensive. Uh, so so let's look at this function. Let's look at this function. Now, we could write that as y equals the square root of x, or x to the 1/2 power, because when you raise something to the 1/2 power, it's the same as taking its square root. When we graph that function, its graph is pretty special. This is where we start getting into domains that are restricted. Let's think about a table. What's the square root of 0? 0. So the graph does actually go through the point 0, 0. Is everybody with me on that? Okay. What's the square root of 1? 1. So the graph goes through 1, 1. What's the square root of 4? 2. So the graph goes through the point 4, 2. And 9, 3, but we don't have enough room because I picked the wrong graph. What about the square root of 1/4? What would that be? Square root of 1/4 would be a hizzy. Square root of 1/4 is a half, okay? So the graph looks like it does something like this on the right side of it. So we do know that it goes all the way out to positive infinity. Is everybody agreeable to that? Is everybody good with that? Okay. What happens if we pick -1? What's the square root of -1? It's imaginary. Is that going to show up in the plane? No. So what's the domain of this function then? The domain's not I to infinity. The domain of this is from 0 to infinity. And what do we do with that 0? Do we put a parenthesis or a bracket? It's a bracket on the 0. Great. Okay. How are we doing so far? Okay? Is this making sense a little bit? Am I excited for the end of the school year? Not yet. I'm not counting down until my brother's birthday. On the day he was born is when his birthday is. That was a smart aleck answer. May 20th, that's when I'll start the countdown. So here we go. For any functions, f of x and g of x, and the operations f of x plus g of x, f of x minus g of x, and f of x times g of x. The domain for all operations. For the domain for all operations is the union of the domain of f of x and g of x. I know this is going to seem a little overwhelming and confusing. So we're saying f of x is any function, g of x is any function. When we add two functions, when we subtract two functions, when we multiply them, finding the domain is quite simple. The domain of the resulting function is the union of the domain of each function. Might seem a little weird, but it's really not that bad. It's not that bad to the math overlord, or it shouldn't be that bad to you either. And here in a minute, I'm going to fire up the TI Nspire, and we'll look at some functions, and we'll examine them. Okay. How's everybody feeling so far, all right? What's my favorite food? I could live the rest of my life eating cheeseburgers every day. If it was breakfast, it would have to be cheeseburgers with eggs and maple syrup on them. And if it was dessert, it'd have to be cheeseburgers with chocolate sauce on them. So, would there be cheese on the cheeseburger with chocolate sauce? Well, of course. It wouldn't be a cheeseburger otherwise. I would pour chocolate sauce on it like I would mayonnaise on it. Hot dog shop's the place to go. Here we go. Example 4. F of x is x squared minus 5. G of x is the square root of x. Find f of x plus g of x and its domain. Find f of x minus g of x and its domain. Find f of x times g of x and its domain. So this really shouldn't be that bad. And I know some of you are thinking that those combinations of food are gross, but there's the whole sweet and sour thing. Sweet and salty, yeah, like the caramel chocolate with the sea salt. Yeah. So let's take a look at this f of x plus g of x. It's just going to be x squared minus 5 plus the square root of x. None of those terms are alike, and consequently, we really can't combine them. Maybe you'll want to switch up the order a little bit, but it's okay the way it is. When we find f of x minus g of x, that's simply going to be x squared minus 5 minus the square root of x. Okay? What's that? These are complicated, you think? That was sarcasm. Okay, so f of x times g of x is x squared minus 5 times the square root of x. We could simplify that, but it gets kind of messy, and I honestly don't care if you could distribute that and simplify that. What I do care about is this. I do care about the fact that we can find the domains. Okay? So let's back that thing up. Speaking of backing things up, if I could take this moment to just air out a pet peeve of mine. Anybody have pet peeves? So, 12 years ago, delivery people, FedEx, UPS, would actually take their big trucks and pull them into people's driveways and not leave them parked in the middle of the road for 10 minutes at a time. And landscapers 12 years ago would take their landscaping rig with the truck and the 22-foot enclosed trailer, and they would actually pull it into somebody's driveway and back it out back onto the road instead of leaving it parked in the middle of the road. I don't understand how people can't back trailers nowadays. I don't know what happened in the last 12 years. But I saw an epic fail on my way home the other day. Somebody took their, you all know what a pontoon boat is, right? Somebody took their pontoon boat and they went to pull in their driveway and they missed. And so the one axle fell into the ditch. It was pretty bad. People can't drive trailers anymore. I don't get it, but whatever. So anyway, here we go. I'm not great at it, but I could back a trailer in and I wouldn't park it in the middle of the road. I would park it 3 blocks away and ride down the road rather than block the middle of the road. So anyway, here we are. The domain of, what's the domain of this function? What's the domain of that function? We need to know this. It's not -5 to infinity. We're not talking about the range. We're talking about the domain. -infinity to infinity. Okay? So what about the domain of this one? What's the domain of this one? We just saw this one a second ago. We should remember this. 0 to infinity. And is it bracket 0 or parenthesis? Bracket 0. Okay. So let's think about this. With domain, sometimes it's easier to think about what x can't be than what x can be. Let me say that again. With domain, sometimes it's easier to think about what x can't be, cannot be, rather than what it can be. I'll say that one more time. With domain, sometimes it's easier to think about what x isn't allowed to be rather than what x is allowed to be. So let's go to each of these functions, starting with the sum function. What's the domain of that sum function going to be? It's not going to be negative infinity to infinity. It's going to be what? 0 to infinity? Parenthesis or bracket around the 0? It's still going to be the bracket. Okay? So the deal is, if we just look at, let me get my star out here. I don't know if it's going to work so well. You know what? I got something better than the star. I want my magic marker. Okay. So if we look at this function, that function has no restrictions on it. Okay? There's no restrictions on that part of the function, but all of a sudden, now you know what? This thing's not allowed to go. This thing's not allowed to go into the negative realm. And this is part of this, so the whole thing is restricted to that. Think about this. Think about you're going out to the party with your friend, okay? And you're allowed out as late as you want, but your friend has a 1 o'clock curfew. And you're with your friend, and you're responsible for your friend. Because your friend has a 1 o'clock curfew, you have to take your friend home at 1, right? So you have a 1 o'clock curfew when... Does that metaphor help make a little bit more sense of this, though? Okay, good. So what about f of x minus g of x? What's the domain of it going to be then? It's still going to be 0 to infinity. And what about the domain of this product? The same thing. It's going to be 0 to infinity. Now, I know some of you think that I'm just rifling off whatever. So let me bring up my calculator. In this moment of time, I'd like to give a shout out to the future Mr. Minnick. I'd like to give a shout out to anybody watching back at home. I'd like to give a shout out to my younger twin. I don't know if you all know who that is, but I know who it is. Anybody want to give any shout outs to anybody else? Will Duvall. To know his dad because he is really good at backing up trailers and doesn't park in the middle of the road and is not a menace to society. I would give a shout out to him too. You're welcome. Anybody else? Shout outs? Lauren Jones? Harold and Kumar? I don't know who those are, but. Okay, so here we go. So on this graph page, I'm going to go ahead and add f1 of x is going to be, what was it, x squared? Was it x squared minus 5? Okay, and this one was the square root of x. Okay, now I'm going to go ahead and add a third function. Check out what this third function is. It's going to be f1 of x plus f2 of x. Does that make sense what I did there? Check it out. Notice how that function, if I were to look at a table, notice how that function doesn't go to the left of the x-axis. Is that real clear? So let me see if I can go back for a minute. Let me see if this calculator is going to let me do what I want to do. I don't want to see the graph of the square root function. I don't want to see the graph of the other one. Okay? So again, do you see how the domain is restricted? Okay, check it out. Let's go to the next one. Let's go f1 of x minus f2 of x. That's kind of interesting, isn't it? And let's go one more time. Let's go with f1 of x times f2 of x. So each one of those looks a little bit different, but they do all have the same domain. Is everybody okay? Comments, questions, concerns, short debates, long debates? Regardless of what they are, they're all going to have the same domain. So if you have no restrictions, you have no curfew, you're allowed to do whatever you want, but you're hanging out with your friend who has a 1 a.m. curfew, because you're hanging out with him, you have a 1 a.m. curfew. Okay? Okay, let's go to example 5. Example 5, for f of x equals x squared minus 5, and g of x equals the square root of x, find g of x divided by f of x divided by g of x, and their domains. And this will be the last thing we do today, I promise. Tomorrow we're going to talk about composite functions. There's a long debate real quick? Well, a long debate wouldn't be real quick. We're not done with the notes yet today. There's a long debate. It's going to have to wait until we get through this example. Here we go. G of x divided by f of x is going to equal what? Well, what's g of x equal to? Well, what's g of x equal to? It's given. The square root of x over x squared minus 5. That's it. That's it. Well, that wasn't bad. We're not done because we haven't talked about the domains and we haven't done the other one. What about f of x over g of x? X squared minus 5 over the square root of x. Okay. Let's go back for a minute. Not for a minute, literally. Here I said if the operations are addition, subtraction, or multiplication, the domain is simply the union of the domains, right? Did I include division on that list? I didn't include division on that list. Well, let's see if we can't find the domain of this first function. Negative infinity to 0, it's not that. It can't be 0 to infinity because I already would have told you, so it's not that. Infinity to negative infinity can't be that. It's x to infinity? That doesn't make much sense, but no, it's not that. Maybe we should look at the graph and see if we can't figure it out. Maybe we should look at the graph and see if we can't figure it out with the graph. So let's go to the graph. So I don't want to look at the graphs of everything that I've graphed before. Now my f of x was this x squared minus 5. So in the first one, I want f2 of x over f1 of x. Okay, so I want f2 of x over f1 of x. So f2 of x over f1 of x. And check that out. That's kind of odd looking. Um, something unusual is happening. Let me try inserting a table. And my calculator is going haywire. X isn't allowed to equal anything more negative than negative 1. Whoa, what's going on over there? It can go through 0. This is very interesting. Let me try something here. Now this is F6, right? Let me insert a calculator. F6 of negative 1 is non-real. Let me try F6 of the square root of 5. That worked. That's surprising that it did. It's real surprising that it did. So the domain here isn't all real numbers. The deal with the domain is x is not allowed to equal, well, x has to be greater than or equal to 0 because of this part right here. And according to a theorem, according to a law, according to the rules, maybe I didn't put those functions in right. Let me go back here and look at something for a minute. Get rid of the table. Tab. And I don't understand why my calculator does this. It gets haywire here for a minute. F2 of x over F1 of x. Oh, my F1 of x changed. That's why. That's why. That was supposed to be x squared minus 5. That explains quite a bit, actually. Okay. So back on this calculator page, remember when I found F6 of radical 5? That is undefined. F6 of negative radical 5 would also be undefined. So the domain is this. X is not allowed to equal negative the square root of 5. X is not allowed to equal positive the square root of 5. For this second one, who thinks they could find the domain on the second one? X isn't allowed to equal negative square root of x? No. It's the same as the one above it? No, it's not. X is less than or equal to 0? Nope. All real numbers? Nope. Nope. Hold on a minute. What is that one thing? What does the square root thing say that it can't be? The square root says that we can't have any negatives, right? So you're thinking that it's going to be from 0 to infinity with a bracket on the 0, right? But watch. Watch. Let's go to the graph. So real quick, let's check the domain on this one. Does this function exist when x equals 0? Does this function exist when x equals 0? No, it does not. So the domain here is actually from 0 to infinity, and we don't count 0. Okay? Okay. So the deal is, if we have f of x over g of x, f of x over g of x, the domain is this. The domain is the union of the domains of f of x and g of x and g of x not equal to 0. Who could tell me why g of x is not allowed to equal 0? Because it's in the bottom, and what happens if you have 0 in the bottom of a fraction? It's undefined, right? Okay. So we'll try another couple of those tomorrow, and tomorrow we're going to be talking about composite functions. It's been real, it's been fun. See you next time.